tough lecture. This morning loved it. So where we ended on last week was looking at orbitals. Okay, ultimately our electron homes. And I put up this diagram. And ideally, I would have this diagram on every single slide so we could keep constantly referring back to it. So get this kind of locked in your head on what's happening with it. We're going to add some information to it as we go. So Bohr went through and looked at the energy levels. That's what explained our atomic spectra, the atomic line spectrum. So we could take electrons from those individual energy levels, and as they transition between a higher energy level to a lower energy level, that energy loss happened to be in the form of light. Okay? And that's what gave us our atomic spectra. This ended up getting further refined into our orbital types and orbital orientations. Okay? So our ground state is in the black one. Okay? So I hesitate using symbols, but I'm going to start. No, I won't. I'll avoid doing that. Energy, lowest energy. This is energy number 1. Okay? Our energy level number 1. Next one up would be energy level 2, 3, 4, and so on. Okay, all the way up. 6. I skipped 5. Let's just scribble. There we go. Okay. So it turns out that each of those energy levels can be broken up into separate types, or different types of orbitals, for lack of a better word in this case. Okay. As we add an energy level, we add an orbital type. So when we start at our lowest energy, we only have one orbital type. When we increase in energy, we get another orbital type, and we get 2 possible types that come out of that. Okay? As we add another energy level, we get a new energy type. Okay? So the idea is that we're slowly breaking these down into the individual sections. We start at our energy levels, then we see we can get some orbital types, and then the next part of this, which is the confusing part, or can be confusing part, our orbital orientation. Okay? Which really gets us to how many orbitals there are possible. So at this point, we haven't even specified how many orbitals we can get. We just said we have different types at different energy levels, and now what we're going to start to get into is the orientation, which generates the amounts of orbitals, or the locations that we can put electrons. Okay? Ultimately, with all of these energy levels and stuff, they're a way of representing where the electron lives. So it's an address. Okay? So try and think of it in that fashion as far as describing where it lives. And there's rules behind that. Our electrons, when first put in, are going to live where? They're going to go to the lowest energy, which happens to be where relative to the nucleus? Closest to the nucleus. Why would they go closest to the nucleus, and why would that make it the lowest energy? Getting towards the right ideas on normalized, the bigger word would be neutral. We took something that was negatively charged, and we're now bringing it towards our nucleus. What charge is our nucleus? Positively charged. The negative and positive cancel out. Everything in chemistry drives or strives for neutrality. So the closer we can get that electron to our positive charge, the more neutral it becomes, or effectively the less negative. Okay? It is still, in actuality, negative, but our appearance of it changes. Okay? So our orbital types, we get 3 possible types. Okay? And these are 3 of the possible types. We can get some more. Okay? These shapes come from solving Schrodinger's wave equation. And not a big thing to memorize, but it's something that's kind of cool to know about. Someone was able to propagate all of the mathematics behind how electrons move and exist, and somehow, in the process of doing all of that mathematics, generated probability diagrams. Okay? Those pictures, or those diagrams of where an electron might exist, happen to give us shapes as shown here. Okay? So what you need to be aware of is not so much that these are your probability diagrams, but that these are what our orbitals effectively look like. And they just predict the electron exists within that space, okay, to a 95% probability. Okay? This is only what our electrons are. Order we'll look at in a little bit.
So these aren't orbital levels, like specific different.
Not specific orbital
This is
levels.
what it could look like.
These are your types of orbitals.
Okay.
Okay. We'll look next at the orientations and how that applies back to the energy levels in a second.
Okay.
Okay. So since these are our possible types, so as we increase in energy, we're going to start to get more and more complex. Which of these do you think is the lowest energy?
The circle.
First one. Why?
It has the fewest dimensions.
It's the least complex. Okay. I don't know if I like the fewest dimensions, but that's possible as well. Okay, it's the most simple. It doesn't matter which way we spin it. It looks the same. You could spin it on your finger, make it fun, that kind of fun stuff. We can't do that as easily with the other ones. Okay, they look more complex. This first one, we could come up with a name for it, okay, or a couple possibilities. First thing we could do is a description of it. How would you describe that orbital? What does it look like? It's like a sphere, so we could call it a sphere. Sorry, that just looks weird to me. I'm going to fix that. Okay, between the next two, this was our lowest energy potential. Between the next two, which one do you think is lower in energy? It's a little bit more difficult to process. Still the leftmost one. Okay, so our rightmost one is probably our most complex. All sorts of weird different lobes coming off of that. Within an individual energy level, that's going to be our highest energy. Okay. So with our lowest energy, we called it a sphere. What can we call the next one? Infinity symbol. It's not a bad one. I've heard that one before. Remember, this is 3 dimensions, though, not just in 2 dimensions of the infinity. Well, yeah. Okay. So if we scale this up, the typical name associated with this, did I spell that right? There are 2 B's? It's a dumbbell shape. Okay, or at least I can say it right. It's a dumbbell. Okay. What's the last one look kind of like? Looks kind of like our clover leaf. Okay. I do expect you to know what these shapes mean relatively. So on the test, I could give you the s orbital, or that image as a shape, and say, what orbital is that? You would tell me the orbital name, which we haven't specified yet. Okay, so I do expect you to correlate the shapes with their names. What if I said, which orbital is the dumbbell? Well, of these 3, which one's the dumbbell? Middle one. Okay? You're responsible for matching those shapes to the correct names that we're now going to put into them. So scientists and predominantly chemists tend to not like words, as you can see when I stumble over the words that I end up speaking. So we want to simplify it a little bit more. We're going to come up with another name for these. Instead of describing how they look, because we could get different answers, we need to come up with a specific name. All right, so what do we pick for our first one, our lowest energy? Sphere is called what? The s orbital. S for sphere. That seems reasonable. The dumbbell shape is known as what? What do we call that one? Not a bad guess, except in German, dumbbell apparently begins with P. Made that up. I don't know if that's true. But the dumbbell shape is definitely your p orbital. When we move to the clover leaf, what do we call that one? There's your d orbital. Okay. So the orbital names don't necessarily match the shapes of those. So you're going to have to separate the shapes out. Always correlate your sphere to the s orbital. Your dumbbell shape is always going to be your p orbital. The clover leaf is always going to be the d. Okay. And when we start looking at these, we'll come up with other reasons why we don't want to use the shape as our name identifier, okay, which we'll see with the d orbitals. I went through and ranked these as lowest to highest energy. What's my next slide show? So if we went back and looked at that energy diagram, what orbital are we going to have for our lowest energy, our black energy? Only going to be the s orbital. We will not have p or d because there's only one energy level, one orbital type. So we just get the s. What happens when we move up to our blue energy, our second energy level? Okay. We're always going to keep the orbital that we had previously and add one. So at our second energy level, what orbital types do we have? S and P. Okay. What happens when we move up to energy level 3? We'll have S, P, and D. You'll notice that when I put those extra lines on, I did separate them by a small distance. And that's because there is a subtle energy difference between them. And that becomes really important as you move further through the periodic table, mainly towards the bottom of it. Makes things a lot more complicated. Okay? So now we get the general idea of both our energy levels and our orbital types. The next issue on this is our orbital orientation. But potentially before we start that, what's up?
There's only 3 orbital types, so you could only go so far.
So good question.
Yeah.
When we start at energy level 1, we just have the S. Energy level 2, we have S and P. Energy level 3, S, P, and D. When we move to energy level 4, how many orbital types do we need to have? 4. How many orbital types do we have at energy level 4? 4. Interesting. Why did I not show that fourth one?
It's imaginary.
There we go. Okay? Not even hard to understand, it's hard to draw. Okay? So it's not easy to put that image together. Feel free to go use your own time to find the fourth energy level or the fourth orbital type. What happens if we go up to energy level 5? Now we need 5 orbital types.
Are there 5? Is there like an infinite amount of them? Like,
We have the potential for an infinite amount.
wow.
Okay? That said, as we go up in energy, what ends up happening? We start putting the electrons further and further away from the nucleus until eventually what happens?
They're free from
They're completely free from the atom. So we do have the potential or the theoretical possibility to increase our orbital types infinitely, but eventually we get so far away from the nucleus that the electron is effectively not attached to the nucleus anyway. Now it's no longer part of an orbital because it's not attached to the atom. Okay? So there is kind of a limit to the amount that we end up seeing. Turns out the limit that we have reached so far with our elemental abilities is only up to the f orbitals. Okay? We haven't exceeded that limit. Okay? At least I don't think we have.
But we're only going to be responsible for the 3 orbital types.
So the orbital types that I would expect you to know by shape are those 3. Your S, P, and your D. Okay? I won't worry about the F, though if we added the F, in theory, you should be able to predict it. Okay? If I gave you a new shape, okay, and it doesn't match one of these, what orbital should it be? Probably the F. Most certainly not the S, P, or D, because it didn't match the ones that you know. Okay? Make sense? So you can do kind of a process of elimination on that. The next issue comes in with the orbital orientation. Okay, so the next layer of difficulty that we can process into this. Every orbital has the potential to orient differently in space. If it does orient differently in space, that generates a different energy state, and we have a new orbital. Okay? So let's take a look at the S orbital first. All right, what orbital is this? S orbitals. It's a sphere. If I rotate that sphere, does it look different? No. So we don't have any more energy states. There is only one for the S orbital. Okay? So if we went all the way back to our lowest energy state, what's our orbital for our lowest energy state? Our S. There is only that one S orbital. That's it. Okay? It does not break into smaller ones, which kind of becomes an issue because that can only account for a certain number of electrons before we now have to move up to the next energy level. Okay? And so on and so forth. Need to go one more. So, one possible orientation for our s orbitals. Uh-oh, there it goes. What do we end up with here? What orbital is this one? It's a p orbital. Okay, what happens if I take that p orbital that's aligned now on the x-axis and I rotate it so it's now aligned on the z-axis? Does it look different? So if I take my hands here and I turn them, does it look like my hand is in a different position? Yep. What does that mean? There's another energy state or another type of orbital. What happens if I rotate it once more? I have another one. How many orientations do we get for a p orbital? 3. I know where you want to go with that, but don't do that. Okay. We get 3 possible energy states. You'll notice that the drawings are attempting to draw these orbitals on those individual axes. Okay. So we could refer to the class, okay, or go through and start to label these. We've got our s orbital here, and we move to the next one. We could label these as our p orbitals as a group. Okay, and now we've got some interesting dynamics that we can add to this. How many electrons can fit into an individual orbital? We did briefly talk about it. Go ahead, I hear you.
2.
It's 2 electrons. Okay. Electrons repel each other, so we want to limit the amount of electrons in any individual orbital. If we go all the way back again, remember I said that last thing that we could look at is electron spin. If we spin the electron one direction and spin another one the other way, they stabilize each other out and they can actually coexist. Without that spin, they can't exist in the same orbital. Which means within an individual orbital, the most we can put in is 2, because we really only have 2 ways we can spin it, clockwise or counterclockwise. Okay? So what happens when we move up to our p-type orbitals? How many electrons can fit in a p-type orbital?
There's more ways to spin it because it can go.
Within an individual orbital, how many electrons can you put? 2. What happens with our p-type? We get 3 possible orbitals. How many electrons can potentially go into p-type orbitals? 6, because we get those 3 orientations. Another way that we could specify this is instead of calling it just the p-type, and you can see this as a subscript underneath each of these, that first one is a p-type where the p orbital is on the x-axis. And the next one is a p-type on the y-axis. And the next one's a p-type on the z-axis. So when we go through and look at each of these orbitals, we could classify each one as its own individual state. So when we start to look at what we'll look at in a little bit, electron configurations, we can start to call this S, PX, PY, PZ. Okay? The X, Y, and Z's are all still applying to p orbitals, and that can get a bit repetitive. So typically, if we were going to look at a configuration, we simplify and just refer to them as the p-type. Okay? And we'll look at the amount of electrons in p-type orbitals instead of specifying the X, Y, and Z. Okay? We'll see again in a little bit when we start to look at electron configurations why it's nice to simplify to the p. Okay? Questions about that? Okay. Last orbital type that we're going to look at. What orbital type was this? These are our d orbitals. Okay. You'll notice that these orbitals are oriented in a very particular three-dimensional space. Again, it's not easy to draw. Okay. We can take those same orbitals and change their orientation in space, and we can generate 4 new or 4 more orbitals. And what we end up with the d orbitals is 5 potential orientations of our d orbitals. Okay? Remember with the p orbital we had 3 orientations, and we could refer to them simply as px, py, pz. When we move to the d orbitals, we're adding that extra plane. So now we can't refer to it being only on the x-axis or only on the y-axis. We would have to refer to them being on 2 different axes. which means instead of referring it to as a px or py or pz, we would have to call it a dxy, a dyz, a dxz. Okay? That gets a lot more complicated and a pain in the butt to deal with. So what ends up happening, again, the same idea as with our p orbitals, we simplify and refer to the group as d orbitals. Okay? And we won't break them down into the individual orbital classes. So the next question, within a d-type class, how many electrons can we fit? 10. Each orbital gets 2 electrons, 10 electrons go in. Okay? So what you're responsible for are recognizing what the orbital is based on its shape, how many different orientations you get. So for the S, it's how many orientations? 1 for the P, for the D, 5. Okay? And relatively the shape. Why do I say relatively the shape? Changes a little. Okay, I'm going to circle something here and say, did that really only change a little? No, that one changed quite substantially. So it's not as easy to kind of nail down your d orbitals as far as the shapes go. That said, I told you you're only responsible for the S, P, and D. Okay? So if I put that structure on your test, is it the S? Is it the P? You might have a little question there because that looks like a dumbbell, but what's in the middle of it? We got a little saucer or a donut on it. Okay, this is a dumbbell donut. Is a dumbbell donut a p orbital? Nope, which means it must be
D.
What'd you say? D, as in dog. Okay, I heard B as in boy.
D.
Okay. We're looking at a D orbital.
And so the D orbital has a possibility for 10 electrons?
10 electrons can go into it.
Why is it 10?
Why is it 10? How many electrons fit in this orbital? 2. How many electrons in this one?
Okay.
Does that make sense?
The, like, thing.
No. Okay. So now we've got kind of the idea on all these possible orientations, and what we're going to hope to do is be able to put this together to determine where an individual electron exists within any given element. Okay, and that's where we're getting to with electron configurations. Okay, so we went back to this as kind of a summary slide again. We're looking at each of our bulk energy levels. It's a good thing I included that. So we could say, above all my colorful lines, we've got our energy levels that then break down into our types of orbitals, which then breaks down into our orbital orientation. And orientation is too long of a word. Our orbital orientation, which really gives us the number of orbitals. Okay? So as we move through our energy levels, we can start to see how we can build larger and larger structures by adding our electrons in. Okay? And we got some rules as far as we put our electrons into these homes. We're always going to go lowest energy first, and we're always going to pair within an energy level, an energy, before finding a new home. Okay, so what do I mean? Let's start at hydrogen. How many electrons does hydrogen have? Okay, 1 electron. So where do we put that 1 electron on this diagram?
Closest to the nucleus.
Which, in this case, since we haven't specified where our nucleus is, lowest energy, bottom. So we could put in our electron at the lowest energy. Okay. If we move up to helium, what happens now? Helium comes in with 2 electrons. Okay. So we're going to have to add an electron to our diagram. Where do we put that electron?
Above the blue line.
If we jump up to the blue line, we have now jumped in energy.
Oh, it
Okay.
contains 2 electrons.
Each orbital holds 2 electrons. So we will pair before we jump in energy. So helium puts an electron at our first energy level. What happens if we move to lithium? We'd still have the 2 electrons for our hydrogen than helium. With lithium, we have 1 more electron. Can we fit it in our lowest energy? Nope. So what do we have to do? jump up in energy. Remember, once we jump up in energy, we split into possible types of orbitals. Which orbital was lower in energy, S or P? S. Where does the electron go for lithium? Stop playing. It'll go into our S. What happens when we move to beryllium? One more electron. Where does that one more electron go? Still goes into the S because it's lower in energy. Boron. Now we can jump up to our P energy level. How about carbon? Goes into the P, but which P? What was our rule? We want to pair before finding a higher energy orbital. According to our chart, what's the energy of all of those P orbitals? The same. So where should that electron go? To an empty one. Okay. Those electrons, or all of those orbitals, are the exact same energy. We want to pair before we jump in energy. I know that doesn't super clear that. Okay. Before we move up in energy, we want to pair. Are we jumping in energy to put an electron in the same energy level? No. So then the question comes, okay, do you want more space or less space? More space. What's our electron going to do? It's going to find more space before it goes into a higher energy state. So what happens with nitrogen?
So why wouldn't you put two of the red lines or whatever in the one?
If we put it in the one, are we giving it more space or less space? Less space, because we're now crowding it with another electron.
So we did that with all the other ones.
We did that with all the other ones. Did we have an energy equal to or lower than we had in the other ones? Okay. In this case, we have an unavailable orbital that's actually the same in energy.
Okay, but so then say if we have another one, and then we have another one.
So we do nitrogen, where's that electron go? The last available orbital. Now you got a good question. Move to oxygen.
You start doubling up those ones?
So now what do? We're going to double up because we're going to, instead of doubling up, what's our other option? Jump in energy. Double before jump. Okay.
So we have to like maybe fill out something like this, kind of like on the exam.
Kinda, sorta. Okay. Yeah, kinda, sorta as far as this goes. We're going to do some tweaks on that. The main reason I'm breaking this down is because that explains some of the periodic trends that we'll talk about a little bit later too. Okay. So I want you to have the baseline for understanding that first. What element do we currently have drawn up there?
Helium. Or hydrogen. Oh, I see what you're doing. Oxygen.
Why oxygen? We counted all of those electrons. Okay, so we're looking at 8 electrons drawn into that. We're looking probably at the element oxygen. Okay, it's kind of a trick question because do the electrons define the element? No, officially we need to know the protons. At this point, we're assuming everything's neutral, stable, so every time we add an electron, we're also adding a proton to it. Okay? So, another kind of summary, each orbital can only hold 2 electrons. So if we take a look at our first energy level, it's about to cover up the 1s on my iPad. That would have been awfully silly. How many orbital types do we have for the first energy level? The first energy level gives us 1 orbital type. That 1 orbital type is S. It's the simplest, the most symmetric, nice and easy to deal with. Okay? How many electrons can we put into an S-type orbital? 2 electrons, because there's only 1 possible orientation. So if we now look at the energy level, how many electrons did we put into that? Total of 2 electrons went into the 1, or energy level 1. What happens if we moved up to our second energy level? How many sublevels do we have? Okay. So sublevels are the types of orbitals. How many types of orbitals do we have?
Do you include the other one?
So when we jump up in energy levels, we started at our 1s, okay, our energy level 1. When we move up to our second energy level, how many types of orbitals are there?
4.
How many orbitals are there?
4.
4. How many types? 2. What are those types? S and P. Okay, makes sense? So we're trying to distinguish types from orientations. Okay, I know they're very, very difficult to align or very easy to miscommunicate there.
Okay, so say that again. How many are in that one?
So let's go back to the next sequence. If we go to energy level 2, what sublevels or what types of orbitals are possible? S and P. There are only 2 types. We started at energy level 1, we had 1 type. We moved to energy level 2, we add an extra type. We're now at 2 levels, or 2 types. So we would call those S and P. Okay. Are those the same S and P that we, or sorry, let's stick with the S. Is that the same S that we had at the 1 energy level?
Yes.
It's in addition to it, so it's not the same. It's the same shape, but it's not the same. What does that mean? I want to distinguish this S in my second energy level from my S in my first energy level. How do I distinguish that? Call it the 2S. So the number in front is in reference to the energy level that we're at. Okay. Where was the p orbital that we're looking at now? This is in energy level 2, so we should call that our 2p. Okay. How many electrons can fit into the 2s orbital? 2 electrons. How many electrons can fit into the 2p type?
6.
Why 6? There's 3 orientations. Each orientation can take 2 electrons. So the amount of electrons we get would be 6 electrons. How many electrons can we put in the energy level for 2? Our second energy level.
8.
The sum of those, 8 electrons. Okay, kind of makes sense? Little shady. Okay, so let's try one more since I think, well, let's see. Is it going to give me everything? Okay, good. It didn't. What happens when we move up to the third energy level? How many types of orbitals do we have? 3. What are our types? P and D. Is that s orbital the same as we saw in our second or first energy level? No. How do we specify it? 3s. So we're specifying the energy level of that new orbital. How many electrons go into the 3s sublevel?
2.
How many electrons can go into the p sublevel?
6.
How many electrons can go into the d sublevel? Why 10? 5 orientations. Each one can hold 2 electrons. We've got 10 electrons. How many electrons per our energy level? 18. Coming a little bit more solid? Based on the chorus, I'm going to kind of guess yes. Okay. You could go through and propagate this out for your S as well. Or sorry, that's not what I meant. 4, energy level 4. You could do it for energy level 5 and 6 and 7 and so on. Okay, so you can propagate that out and see how many electrons you can get in. Okay? So the next big part of this, I'm trying to sort of delay as I walk around to make sure we're hitting the next big part, is how do we actually put the electrons in? Okay, we started to discuss that. Oh, I'm going to regret doing this. When we looked at our energy diagram, we started putting our electrons in sequence-wise. Okay? And one of the trends that was found is that, yeah, it does seem to go by energy level. First, then second, then third, then fourth, then fifth, then sixth, and so on. Turns out it doesn't quite work perfectly. Okay? And the reason is that as we get closer and closer towards our higher energy shells, what ends up happening? These split into those separate orbitals, but then the higher energy also splits into separate orbitals. We're running out of space to stack those orbitals, so what ends up happening is instead of having discrete energy jumps or big energy jumps between these, we end up seeing smaller and smaller gaps. That smaller and smaller gap starts to introduce the next issue. Instead of doing just based on energy level, it also goes based on symmetry. Okay? We said the S was the most symmetric. Doesn't matter which way we spin it, it looks the same. Okay, so our s orbitals, as we get further up, start to actually drop in lower energy than some of our higher order orbitals, like our d's or our f's. I know, ridiculously confusing, okay, but that's what ends up happening. So we want to come up with some way that we can sort of organize that so that we know that when it fills, we can account for that loss. Okay, and that's what this next diagram is trying to show. This is why I said I'd regret it. It takes too long. What's that?
I just zoned out and then you said it's kind of confusing, so I kind of stayed.
So what we're looking at is kind of the same thing that we just drew out. Okay? What we're starting with is we write our first energy level. We have only one type, 1s. Second energy level should be drawn where? Higher or lower? Higher because it's higher in energy. How many orbital types do we have for our second energy level? 2. 2s and 2p. Drawn on the same line. We move up to the next energy level. How many types do we have? 3. 3s, 3p, 3d. For our fourth energy, s, then p, then d, and then technically it didn't show up f all the way out on the other end. Okay? So how this is going to become important is how we start putting our electrons in. Okay, so let's pick a couple examples. I was kind of mean because I didn't give the morning class a good example for this. Let's pick my favorite atom. Let's go with carbon. So if I asked on the test for the electron configuration for carbon, what's your first step? Okay, I would argue against filling up the first set because that implies that you knew some other information. What's the other information you need to know? You need to know how many electrons there are in it. How do you know how many electrons there are? True. What's that? We'll assume neutral, yep. How many electrons or protons does carbon have? Stop looking, you're cheating. What did you have to know to find carbon? You needed to know the symbol, okay? You still have to know those symbols. So we could start off with, by writing our symbol down, we're looking at carbon with a C. How many electrons do we need to account for? 6 electrons. Why E minus? Electron begins with E, and they're negatively charged. There we go. That's the notation. So we now want to start putting electrons into our carbon. Where do we put our first electron? The lowest energy first. Our lowest energy was 1s. Okay, how many electrons can go into the 1s? 2 electrons. So we can do 1s2. Have we accounted for all, I guess I didn't talk about that yet, but that'll work. Have we accounted for all 6 electrons? Nope. So what do we have to do? Next energy level, which is 2s. 2. Next energy. 2p. Whoops. You're right. Nope, you're wrong. It's 2p1. 2. 2. Okay, so let's look at some of this notation. Okay, what did the number in front mean? Our energy level. What did the letters mean? The type of orbital. What's the last number mean, our superscript? How many there are in that individual orbital type. Okay, why show the 2 as a superscript? No, that's your electrons. Why not show it as a, instead of doing it that way, we could have written it just as easily 1s2, 2s2, 2p2. Whoops, I even did that one wrong.
Because you get the values looks confusing.
Yeah, that looks confusing. So we want to separate out the number of electrons in some fashion. Why not do it as a subscript? Where have we seen subscripts before? Say that. H2O. We've already used our subscript notation to refer to the number of atoms in an individual formula. So what we're trying to do is come up with a more consistent fashion. We'll specify our electrons in the upper right-hand corner. It's something that will actually hold true relatively when we get into more complex structures as well. Okay? So our electrons are specified in the upper right-hand corner. How do we know that we've accounted for all 6? Well, look at your subscripts in each of those cases. 2 plus 2 plus 2 gives you 6 if we accounted for all of our electrons. Yeah. Okay. There's another way we could have written this, okay, which requires a little bit more space. Could have gone 1s2, 2s2, 2px, 2py, 1 electron in each. Perfectly valid to go through and do that. Why not? Why would I not draw that out that way?
Because like the hierarchy.
It's confusing is ultimately what it is. We have to add the x and the y, so we are adding information about the orientation. We're adding information on exactly where those electrons are located, but at what cost? Okay. The cost is that it's really easy to get confused. We have to draw a whole bunch more, so we tend to not draw that out. Okay? So, let's try another one. Or do you have questions about that one in particular? Yes?
Does it always go like X, Y, Z? Because they're the same energy.
They're the same energy level, so you can put them in any order you want. Y, X, Y, Z? It's alphabetical. That's about it. Okay. So, next one. Let's pick something a little bit more complex. Let's jump to sulfur. Not O, it's sulfur. I thought it was funny. Someone said O, right?
Yes.
Sulfur, our symbol is S. How many electrons does sulfur need? 16. So already we can be like, oh, this is going to suck. This is going to take forever to draw all this out. But hey, that's what we have to do. It's a problem asked for. So we start putting our electrons in. We put them where? First level. So 1 is 2, 2s2, 2p, 6. Why 6? How many electrons can we fit into the p type? 6. Okay, so since that only gets us to oxygen, or sorry, our p type would only get us to oxygen, we'll have to fill beyond that. So we have to fill that entire second energy level. We can then move to 3s2 and 3p. Okay, since I heard 6. 2, 2, 6, 2, and 6 gets us how many electrons? 18. How many electrons needs to go into that last orbital? 4 electrons. Okay. So when you go through, don't automatically just fill. Put the electrons in and then check your work. Those superscripts should all add up to the number of electrons that you said should have been there, which shows 16. If we did that math right, 2 plus 2 is 4 plus 6, 10. 2 and 4 is 6, so 10 and 6, 16. Okay? So we want to take advantage of that information to help us check our own work. Our superscript number should add up to the number of electrons we totaled. Yes?
So if it had like a big number of electrons, like, I don't know, like 30 or 40, you would just follow like the pattern, the 2, 2, 6, and then
careful. So I don't like that you're saying pattern, because that makes me nervous. There is technically a pattern. It's always lowest energy. So S, how many electrons go into the S? 2. How many electrons in that S?
2.
How many electrons? Electrons?
2.
Anybody see an interesting question there?
Why did you go to 3D?
Why did I not go to the 3D? Oh man, there's the rule. This is why we set this up. Right at that transition between the 3p to the 3d versus the 3p to the 4s, the difference in energy between those transitions is so small that we see a symmetry effect. Okay? Think back to the most attractive person you know, someone that you're super attracted to. Next time you think about them, put a line of paper right through the middle of their face and compare across. Do it in your head. Don't smack it up on their face. That could get embarrassing. And compare the sides of their face. What you'll notice, they're usually really, really symmetric. Okay? What we classify as beauty usually comes back to symmetry. There are some people that you go, old example, Sidney Crawford. She had a mole. Well, that's asymmetric. But how much of the rest of her face was symmetric?
Yeah, but it was a hot mole.
There's the issue. Your symmetry everywhere else is perfect. So sometimes we'll classify beauty as being just slightly asymmetric. Same thing's happening within chemistry. Once we get up to that opportunity where there's now a very little energy difference, we say, okay, which one's more symmetric? The S is more symmetric than the D. We'd prefer to fill the S first. Okay? When that occurs is only when you're kind of mitigated that energy difference. Okay? And that only happens when you get up into the higher energy levels. So when you look at the rest of the orbitals, we filled our 2p before we filled the 3s. Why? The energy jump between the 2s to the 2p is much smaller than the jump between the 2s to the 3s. So there's two competing factors with that. How much of that information do you need to know? Relatively little. What you need to know is that you fill in this diagram. This diagram is how you need to put electrons in, period. I just gave you the reason why this diagram is correct. You can either listen to me or not. This is what you have to do, period. Okay?
So that's got memorization written all over it.
Yes, it does. Okay? But there's other little sneaky tricks that we can get around with, which we'll look at in a second. Okay? Other questions?
When I read this material, there was a huge question that I had on this.
Yep.
And that was like 3 days ago or something. I don't know. It was
That's okay.
3 days ago. And I don't remember what the question was, but it was like there was something about it that, and I'd have to go back and, repeat what I did and reread, and then maybe the question will come back to me.
So what I'd recommend is when you hit a question, write it down immediately. Worst case, email it to me. Best case, when we're talking about it in class, if it didn't click, if you didn't get your question answered, then raise your hand and ask the question directly. Okay, yeah. No, go ahead.
So this is not the same as like just as if you just continued, sorry.
If you just continued up those lines,
That's
no.
not the same.
Because if we went through and did the lines, that's effectively just saying first this, then this, then this. If we do that, what do we hit first? We hit 3D before we hit 4S. According to the fill line, so let's kind of go through with what this is showing, because I will admit it is confusing. We organize this according to a kind of a box grid line structure. We then go on the diagonal. 1S fills, we double back, hit our next diagonal. 2S fills, next diagonal. 2P, 3S. Everything so far is filling exactly as we'd expect. 3P, here's our transition line. This is the one that goes weird on us. We fill the 3P, we fill the 4S before we hit the 3D. Does it get even weirder after that? What's the next one? 3D, 4P, 5S. Wait, we didn't fill the 4D yet. What the heck? As we get further up in those energy states, we start to increase this symmetry effect because the difference in energy between those orbitals decreases so much. Okay? We see a very small energy gap. How much of the periodic table are you going to ultimately be responsible for to be able to do this? Okay. Well, I do expect the 3D to show up in there. But would I really get into the 4D? Probably not, because that's going to be a lot more difficult to deal with. Okay? If you moved into, say, 151, or it would be just 151, they might expect you to know that material and be able to apply in that range. You don't have to do that yet. Okay? What you're trying to get here are the basics so that when you move into 151, you got the rules set up, and boom, 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 we get this figured out. Okay? With a little refresher. Okay? Questions on how we put these together? Sure. Actually, before we do that, take a look at our sulfur line again. Okay, that's an awful lot of stuff to write out. Okay, and as we've discussed on multiple occasions, chemists are ultimately lazy. Okay, and what we really want out of this is to know ultimately how our atoms can interact, what these electrons do. So if we take a look at those electrons, how do we decide which electrons are more important than other electrons? Well, let's think back to what we're looking at. We're taking two atoms, and as we bring them near each other, eventually what could potentially happen? They could collide and bounce away, or they stick. What makes them stick? What's the thing that's going to cause them to stick? Bonds. And what's in the bond? Electrons. The first thing that interacts between those two atoms is the electron clouds. If they start to get close enough to each other where the electrons of one starts to see the other atom and starts to jump across, and the electrons of the other sees the other, what happens? Now they're sharing electrons. They don't want to leave each other, and the other one takes all the electrons. Okay? So what we're concerned about is the outermost electrons, because those are the ones that are going to be most likely to interact with another atom. Okay? So our outermost electrons are going to exist where? And our highest energy level. What's our highest energy level for our sulfur atom? 3, which is going to include the S and the P. Okay, so we do it based on energy level, not strictly based on our energies. Okay, so we include both the S and the P in this categorization. Okay, so those electrons hold a special name. We call those the valence electrons, which is actually on the slide, but if I click next, it's going to erase all my work. Okay? So we want to come up with a name for the other section of elements. Since we called those valence, the other ones are now jealous and want to have some special name. What special name do we come up with? Well, they're located more towards the center of the atom, kind of like towards the center of, say, maybe an apple. It's the center of an apple. Looking at our core electrons. Okay. For our sulfur atom, we don't particularly care about the core electrons. So what we want to do is come up with some notation that can account for all of those electrons without me having to draw them all out. Okay. So we'll ignore the valence for the moment and just look at those core electrons. What element has 2s or 2 1s electrons, 2 2s electrons, and 6 2p electrons? Also known as a total of 10 electrons. Neon. So what we can do is, instead of calling this our electron configuration and doing the complete one, we can say, F this is ridiculous, this is neon, I can't spell, 3s2, 3p4. I can now shorten down that whole section. Why did I pick neon? Had 10 electrons. Okay, so if we're going to apply this to a different element, all I have to do is write out the complete electron configuration, then I can shorten it. Yeah, that defeats the purpose. The whole idea was to not write out the complete configuration so we could come up with a short one. So how did I get to neon? Where's neon relative to our sulfur? It's our noble gas that precedes that element. Okay. So if we were going to look at selenium, what noble gas would we use as our shorthand? Argon, because it's the first noble gas that comes before the selenium. Okay? And we're going to use this again for our d electrons here in a second.
But, oh, so like, if
Okay. All right, so let's take a look at another example here. Let's pick for our electron configuration, let's do chromium.
Okay, I'm sorry.
Yep.
Why don't we just leave it? Why are we, obviously, I know it's because we don't want to write all this out.
That's
but
all it is.
That's all it?
That's all it is. So that notation, when we're looking at most of the electron configurations that we'll see, is not all that helpful, okay? Because it doesn't shorten our work that much. But if I asked you to provide the electron configuration for platinum, do you really want to draw all of those orbitals out to get you the 1s2, 2s2, all of that? If you do, by all means, feel free, go ahead, do it. Fantastic. Good on you. Okay? But it's going to require a lot more effort. So what we can do is use the shorthand to jump backwards. Okay?
So like if you were doing platinum.
Use xenon.
Okay, and then
So-
you subtract that from platinum and then just.
And you just deal with the rest of the electrons within that level. Which brings up an interesting point. Energy levels. Do we have the energy level information on our periodic table? The electron configuration for hydrogen is what? 1s1. Helium? 1s2. What's our next energy level?
Oh, gotcha. That's
2, right? Next element on our periodic table is lithium. What's our electron configuration for lithium? 1s2 and 2s1. What happens when we move to sodium? 3. What energy level is potassium in? 4. Holy crap, yeah, we do have the energy levels on our periodic table. It's each row. Each row is our energy level. That gives us some information about processing and getting through these a little bit quicker. Okay? So let's go through and take a look at chromium. Start to combine some of this information. Symbol. CR, how many electrons? 24. Gotta admit, I'm a little bit rusty with chromium. This could be a bit dicey. Okay? Since I don't want to draw them all out, I'm going to pick the element or the noble gas most similar to it, okay, as far as before it, which is going to give me argon. Okay? So argon's going to fill up and give us that full subshell all the way up to our 3 Ps. Then what happens? We have to drop to the next energy level. What fills after our 3P? 4s. So we would have 4s2. Argon had 18. 2 more electrons gets us to 20. Still not at chromium. We need 4 more electrons. What orbital do we use next? 3D. Why'd you pick 3D? Because that's what the chart says to do. Okay? You have to drop back down to the energy level because that's how it fills. It's that symmetry issue that we talked about. How many electrons need to go into the 3D? 4 more. Boom. Now we got it. Okay? Takes a little bit of practice to get used to the patterns, particularly when you move up into the transition elements. But after that, hopefully that's where your challenge will be. In theory, at this point, you can do all the other ones pretty quickly and easily. Okay, yes?
We can put F on the exam.
I will not put F on the exam. I had enough of a problem doing the friggin' D ones. I'm not going to deal with F. Another interesting pattern that we could note, when we looked at our valence electrons for lithium, sodium, potassium, rubidium, cesium, what were our valence electrons in? What orbital?
What was it? I'm sorry.
Valence electrons, so our last energy level. So 4, what type of orbital? So if you take a look at those, you'll find for lithium, sodium, potassium, rubidium, and cesium, and even francium, that they're the s orbitals. Sorry, I kind of blurred that. s orbitals, as in Sam. Okay, why is that important? Well, let's jump over to carbon. Okay, carbon. If we looked at our last electron, what orbital did it go into? You guys all wrote that answer down, right? P. How about sulfur? P. How about chromium? D. Interesting. We didn't do a whole lot on the periodic table, but there is some interesting groupings on this. There's some more information found within the periodic table. Not only do we have the energy levels, we also know the orbitals. The first two columns are typically known as the S block. Why? When you go to their outermost shell, what is the last orbital type filled? The S orbitals. So if you wanted to get, say, the last electrons for strontium, which row is that in? Strontium, SR. Sorry, that was a stretch. That was my bad. For SR, we're in which row? 5. According to our S orbitals, it's in the second column for our S. 5s2. Done. Didn't have to worry about all the other freaking elements, things in there. Done. 5s2. Okay. What happens if we move to sulfur? We already did sulfur. Let's do phosphorus. Phosphorus is in row 3, and it's located in what's referred to as the p block, meaning the last electrons are going to go into the p orbital. Since it's in the third row, that would be a 3p orbital. And for phosphorus, 3p3. We now have the last electrons in the last orbital. What happens with chromium? Chromium's a little bit weird because that whole 3D issue, okay, because of how it fills. Your transition elements start at 3D and then go 4D, 5D, 6D. Okay? So if you apply chromium, we need 4 electrons into the d orbitals to account for that bounce. To do that, we'd end up with 3d4, exactly as we just saw. So our periodic table actually classifies a lot of these elements according to their electron configurations. Interesting. Mendeleev knew nothing about the electron configurations. What did he know information about? The chemical properties, how that atom reacts with another atom. What did we say first interacted between two atoms? The electrons. The electron configurations contribute to the overall chemistry of the molecule. So they were able to predict electron configurations or relative families of electron configurations based on how they reacted with other molecules, because electrons were the ones that determined that chemistry. Kind of amazingly powerful as far as their predictive abilities and what information we can get out of the periodic table. Okay? Questions about that? Okay, so the last thing that we're going to deal with here are some more patterns that we can pick up, or the last periodic trend, ionization energy. Okay? Ionization energy is defined as the energy required to remove an electron completely from the structure. So we're going to take that electron and rip it out and put it into the vacuum. Okay, so it's no longer attached to anything. How much energy does that require? Kind of an important observation, typically when paired with the next thing we'll talk about. There's some trends that we can pick up in the periodic table. Those trends look at ultimately where the electrons go. Okay, so if we look up a column, let's see, up the column from bottom to top, the ionization energy increases. Why would it increase as we go from the bottom of the periodic table to the top? The electrons are closer to the nucleus. What charge is the nucleus? Positive. The closer we get to that positive, what happens to the overall charge for both particles? It gets closer and closer to neutral. So the further the electron is away from the nucleus, the less it's balanced out, the more reactive it is, the easier it's going to be to pluck off. Okay? What happens when we go left to right in the periodic table? Okay? Well, in that case, we're not changing the energy level. So our electrons are effectively going into the exact same position. Okay? How is that going to affect how hard it is to remove? Okay, well now there's no longer this distance issue, it's how close it is to the positive charge. And what happens as we move left to right across the periodic table? What happens to the positive charge of your nucleus? It gets more because we're putting more protons into it. So what happens? If we put the same electron now near a larger positive charge, what happens to the electron? It gets held tighter. If it gets held tighter, what happens to the energy required to rip it away? It requires more energy to rip that electron away. So having an understanding of what your electron configurations are can predict the ionization energy as a general trend. Also works for the radius. When we looked across the periodic table, did our radius change much? Okay, we didn't get much of a change, but what was our trend? What happened to the radius as we moved from left to right? Got smaller. But we added more electrons. Why does it not get bigger? Because those electrons are being added at the exact same energy level, the same distance away. Your nucleus is only getting more and more positive. It's going to start to draw those electrons even tighter, closer to the nucleus. Hence, your radius goes down as you move left to right. Okay? So an understanding of the electron configurations allows you to then process a lot of these trends. One of the biggest things that I'll note here, particularly with the phrasing put in here, is that both of these start off with "in general." What the freak does "in general" mean? General means it doesn't always work. Okay? But use your electron configurations to predict why it doesn't always work for your inconsistencies. So helium all the way down to radon. So what's the relationship between all of those? They are all where on the periodic table? Same column. So we're looking up and down the column. What would we expect to happen to the energy required to remove an electron from helium versus radon? Okay, we would expect less energy to remove an electron from radon because the electron's further away from the nucleus, not canceled out, not neutralized as much. What's the result? Booyah, yes, works perfectly. Okay. What happens if we look now between lithium and neon? Okay, it would be nice if I could zoom in on this for you, but I can't. What element comes after lithium? So we got lithium at the bottom, followed by beryllium. Energy goes up. Why would the energy go up? There's more positive charge. Stronger nucleus means the electrons are pulled tighter, harder to rip the electron away. What's the next element? Boron. Energy dropped. That seems a bit odd. Then what happens? Goes up again. Why would it go up? More nuclear charge. Goes up to nitrogen. Then what happens? Drops back down again. So we see two oddities in this trend. We've got oxygen and boron being weird. What's the configuration for boron? 1s2, 2s2, and here's where it's helpful to actually break out your p orbitals instead of being, well, actually we don't have to do it quite yet, 2p1. What happens if we remove that one electron? We now have full subshells. That's pretty cool. That's a lower energy state. Everything looks symmetric. So boron says, heck yeah, get rid of that electron. Because if you remove that, I look cooler. I'm more symmetrical. People like me. I don't have a mirror. It would be funny if I had a mirror. Okay. So that's what's happening with boron, why its energy would drop. What happens with oxygen? Kinda. We draw it out 1s2, 2s2, 2p. Wow, you had to say 6, didn't you? 2p4, because there's 8 electrons in oxygen. Well, you move that one electron, well, it's 2p3. That doesn't look all that symmetrical. What did we say was special about your p orbitals? Another way we could have written it out? 1s2, 2s2, 2px, 2py, 2pz. Why is that important? Put in your electrons. 2, 1, 1. What's important about that? I remove that one electron, what do I have now? Perfectly half-filled orbitals. Back to my symmetry. Okay? Symmetry plays a huge role when trying to predict the overall trends. Okay? You'll see those show up more frequently in 151. What I expect you to get are the big ones. Okay? So when we go from carbon to nitrogen, you should be able to tell me the ionization energy there because it follows the trend perfectly. Okay? Shall I keep talking? This is the first time you guys haven't got up and left.